In this lecture, we will see more details about blackbody radiation and the spectral lines produced, for example, by an atomic or molecular gas. The black body, first of all, characterizes heated bodies that re-emit radiation at all wavelengths. For instance, that is the case of a light bulb filament that converts electric energy into light. That is the case of glowing embers, which, due to the heating by the flames, will radiate at all wavelengths. It is also the case of lava ejected by volcanoes. This blackbody radiation is characterized by what we call the Planckian curve, which gives the energy distribution as a function of wavelength or as a function of frequency. The units of this luminance or specific intensity is a power by surface unit, by steradium, for radiation that is emitted in all directions, and optionally by wavelength unit as shown here on that axis, or by frequency unit. These Planckian curves have a bell shape, with an increasing and decreasing slope, and so also a maximum. The position of this maximum can be calculated by deriving the function which gives the luminance. If we do it here as a function of wavelength, we will find that the maximum of the curve will occur at a position that depends only upon the temperature. We have therefore a linear relation between the position of the maximum of the blackbody curve and the blackbody temperature. So here we have a constant in mk. We can have it here in angstrom K, which is more useful with the units we use in astrophysics, in the wavelength range used in astrophysics. We can see here the position of the maximum of the blackbody curve for a blackbody temperature of 6,000 Kelvin, or here for a temperature of 5,780 Kelvin. That is the surface temperature of the Sun, for example. And these curves show different temperatures. Here, 5,500 Kelvin, 5,000 Kelvin, and 4,500 Kelvin. Stars are excellent black bodies, so we can immediately see that lambda max decreases when T increases. We can indeed observe it here. A high temperature yields a peak emission in the short wavelengths, the bluer ones, and lower temperatures result in emission peaks that lie at higher wavelengths, the redder ones. Since we have red on this side of the spectrum and blue on that side, in the optical wavelength range, a hot star will appear blue, while a cold stellar object will appear red. So, of course, this Wien's displacement law, which gives the position of the maximum of the blackbody peak as a function of temperature, can be expressed in wavelengths or in frequencies, depending on whether we express the luminance as a function of wavelength or frequency. In looking at the two equations, we tend to feel that lambda max times T times V max divided by T should be equal to lambda max times V max. Of course, but also equal to C. Actually, that is not the case. If we take the numerical values here, we can see that we have 0.57 times C, and that comes from the fact that BV is not equal to B lambda, but it is equal to B lambda times D lambda divided by dV, as we have shown in a previous lecture, and so is equal to B lambda times lambda square divided by C. Another feature which will interest us is, of course, the total energy, the energy flux density, developed by a stellar object which radiates blackbody radiation. In other words, the whole of the luminance at all wavelengths, or at all frequencies. So once the integration is done, the available energy, once we have integrated the blackbody, for example here, under the orange curve, The result of the integral is the density of the energy flux, which is simply
la densité de flux d'énergie qui est simplement proportionnelle à la température
proportional to the temperature to the fourth.
de proportion qui est évidemment
So we have here a proportionality constant, which is, of course, a power by surface unit and by Kelvin to the -4. As soon as we have the black body temperature, we can determine
rayonnée par une
the radiant power by surface unit at the surface of the black body.
M
So M is simply the power emitted by a unit surface
développée à la surface du
at the surface of the black body.
Alors maintenant, quelle est la relation avec
So
la
now,
luminosité
what is the relation with stellar luminosity?
Cette fois-ci, c'est l'énergie
The luminosity
libérée
is here the total energy freed by the star.
en
The
M.
luminosity will be given in ergs divided by S.
Cette luminosité
This luminosity will be the surface of the star multiplied by M.
de l'astre fois M. Donc 4pi
So 4 pi r square times sigma T4, where we have here the radius of the star.
où on a ici le rayon de l'étoile. La luminosité va être intégrée
The flux M will be integrated on the whole surface,
et M, c'est
and M is the available power by surface unit
par unité de surface à la surface du corps noir. Donc de
at the
l'étoile.
surface of the black body here of the star.
Alors maintenant, nous, au niveau de la Terre,
So now we're at the level of the Earth.
on reçoit seulement une partie
We receive only part of that energy
une certaine distance D.
at a certain distance d.
Donc si on se situe à une certaine distance D, on va
If we are
recevoir
situated at a certain distance d, we will receive a flux by surface unit, the flux F here,
F ici, qui va être L dilué sur une sphère.
which will be L diluted on a sphere of radius 4 pi d square.
Nous, au
So
sol,
the flux we are receiving, we on the ground, is L divided by 4 pi d square.
au carré. Donc ça, c'est reçu sur Terre.
That is received on Earth.
Donc pour cela, F
For this, the unit of F will be erg by second by cm squared,
par seconde, par centimètre carré, puisque c'est dilué sur la surface de la
because it is diluted on a sphere of radius d,
par angstrom dans le cas
and also by angstrom in case we are interested in the spectroscopy,
lumière en fonction de la longueur.
where we disperse the light as a function of wavelength.
Nombreux objets
A lot of stellar objects emit black body radiation.
commencer par notre Soleil,
Our Sun, to begin with, whose surface emits,
l'énergie
in the visible wavelength range, the energy produced at the center of the Sun by nuclear reactions.
produitière,
The dust in the disks of spiral galaxies
chauffée par les étoiles jeunes
is heated by young stars found in the spiral arms,
à gauche, dans l'image
visible here on the right in the optical image of the galaxy.
émise par
This energy emitted by the stars is absorbed by interstellar dust
et réémise sous forme de rayonnement de corps noir
and re-emitted in the form of black body radiation, whose peak is situated in the infrared wavelength, as can be seen here on the image to the right, of the same galaxy, but taken in the infrared wavelengths. One of the most beautiful black bodies is probably the cosmological black body, whose spectrum is shown here as a function of frequency. It is an isotropic microwave radiation which is present everywhere in the universe, and whose origin lies in the Big Bang. The universe, which was extremely hot, extended itself and became colder, emitting an ambient radiation which corresponds now, 13.7 billion years after the Big Bang, to a black body whose temperature is very close to the absolute zero, 2.73 Kelvin.
Alors, ce que vous voyez ici, c'est les points de mesure
What you see here are the measurement points in black,
entre
and the theoretical curve as a solid line.
entre la
You see the theory and measurements perfectly agree.
Le rayonnement de corps noir est certainement
Black body radiation is certainly
en astrophysique.
one of the most common types of radiation in astrophysics. It produces a continuous spectrum. The other type of frequently encountered spectrum is the line spectrum, which we will see in a moment.
Atomique, on les avait déjà rencontrés.
We have already talked about atomic lines in a previous chapter.
Un exemple,
We have taken the example of a relatively hot star here at 15,000 Kelvin.
alors maintenant qu'on a vu le corps noir, on voit que
Now that we have learned about black bodies, we see that a hot star essentially radiates in the blue wavelengths. That is what happens here. We have an extremely steep spectrum in the blue, and we have a continuous one, which is the black body spectrum,
décrit par une courbe de
which is described by the Planckian curve.
position à ça,
Now, on top of that, we have a line spectrum,
d'absorption dans ce cas-là, qui sont dus
with absorption lines in this case, which are due to hydrogen atoms present in the atmosphere,
l'atmosphère, dans les hautes couches de l'atmosphère.
in the upper layers of the stellar atmosphere.
Alors voyons plus en détail.
Let's see in more details the line spectrum produced in this case here. by the hydrogen atoms. For that, let's go back to Bohr's atomic model, where the electron is in orbit around the proton. We obviously have an equilibrium between a column force. We have a proton and then an electron in orbit around the proton. Namely, a hydrogen atom. This is the mass times acceleration. This is just the Newton's law here. Quantum mechanics tell us that kinetic momentum is quantified, and that the kinetic momentum takes an integer value multiplied by a constant. Here we have an integer value times a constant, which is the h-bar constant, namely the Planck constant divided by 2 pi, so h divided by 2 pi. The two equations which we have written in the previous slide are simply Newton's law and a quantification of kinetic momentum, i.e., the fact that kinetic momentum of the electron around a proton can take only very specific values. These two equations will permit us to express the total energy of the electron. So the kinetic energy here and the potential energy here as a function of n and the Planck constant. So an integer value and a Planck constant rather than as a function of the radius and the velocity of the electron. So we have two equations with two unknowns. The solution is trivial. We come back to the total energy of the electron, which will be negative. Since the system is bound, the total energy will depend upon a constant, is negative, and will depend on the energy level characterized by n, which we defined earlier and which is responsible for the quantification of the kinetic momentum. The energy of the electron is quantified. The total energy will depend on an integer value and a constant. We recognize here a lot of physical constraints. The Planck constant divided by 2 pi, the mass and charge of the electron, and the electrostatic permittivity constant of vacuum, epsilon 0. If we express all that in numerical terms, we find that this constant is 2.18 times 10 minus 18 joules. It is an energy. If we convert the result into a more useful energy unit for particle physics or astrophysics, or also for atomic physics, we find negative 13.6 eV. So for the record, an electron volt is the energy acquired by one electron at rest when it is accelerated by a voltage difference of 1 volt. That is the definition of an electron volt. We saw that the total energy is quantified. So we have an energy that is a function of the integer value n and depends on the constant minus 13.6 eV times 1 divided by n squared, where in fact n characterizes the orbit on which moves an electron around the proton. We have a proton here, and then we have an electron that might be on an orbit n1 or on an orbit n2. The electron will be able to go from one orbit to another by gaining or losing energy. If, for example, a photon is absorbed by an atom, the electron will be able to go from the N1 layer to the N2 layer by gaining energy. Conversely, we can also have electrons that are in the N2 layer, an excited layer, and then we'll go back to the N1 layer. The atom will lose energy by emitting a photon with a certain energy hv. What will be the frequency of this photon? We can compute it by simply calculating the energy difference between the atomic layers of the hydrogen atom. For example, the energy difference between layers 1 and 2 can be expressed using the equation we have seen before, 13.6 times the difference of the numerical constants here. So 1 divided by n1 squared minus 1 divided by n2 squared is, of course, in electron volts. It is also the energy that the photons will have once emitted by the hydrogen atoms that will go down from the layer n2 to n1. It is also the energy one has to bring to a hydrogen atom to raise an electron from layer n1 to layer n2. We can summarize here in a figure what happens in a hydrogen atom. We said that we have multiple possible energy levels that correspond each time to an integer value, from 1 to the limit, infinity. We could not represent here all the energy levels between layer 5 and infinity. But if we could zoom in, we would see more and more layers. We can have all possible transitions between a starting layer and arrival layers. For example, to go from the fundamental layer, here, to higher energy levels, one needs energies that will be characterized by photons whose wavelengths are written here. So, if we want energies, high energy differences, we need photons with short wavelengths, so with high frequencies, and therefore high energy differences. Here we have the first series of lines called the Lyman series, which corresponds to all possible transitions between the fundamental layer and all other atomic layers. So if we supply an atom with an energy higher than 13.6 eV, the atom will get ionized. In other words, it will lose its electron. So an ionized gas is a gas transformed into a mix of ions and electrons. So for the Lyman series, we see that the wavelengths are in the ultraviolet. If we play the same game starting from layer 2 to all layers above it, we get the so-called Balmer series, which this time is in the optical range. Finally, if we start a bit further still from the next energy level, we will find the Paschen series, which is in the infrared. Of course, there are other series, going further and further, in wavelength, and to lower and lower energy differences. Now let's go back to the example of a star we had before. The star with a black-body spectrum of 15,000 Kelvin, and whose radiation peak is located in the blue part of the spectrum. So we can recognize here some lines of the Balmer series. The Balmer series is here, and we can see if we want to predict the wavelengths of the different transitions here, that we have, for an example, a line at 4,861 angstrom, which is actually the H-beta line. So this is 4,861 angstrom. So if we look here, we see exactly the wavelength predicted by this formula. If we look at the following line, we have H gamma at 4,341 angstrom, which will be here. The H alpha line lies outside of the wavelength range of the spectrum, so it is not visible. If we went further and further down the blue side of the spectrum, we would have a whole series of lines, here, from layer 2 to all the layers that we couldn't represent. And that would be in this box here. We haven't shown them here, since there would be an infinity of arrows here. That said, we can see them in the spectrum of the star. This multitudes of lines has a limit. Here we have a limit that corresponds to the ionization of the atom. So if an electron is on layer 2, and we provide it with a higher energy than the energy, so to 3.95 eV, the atom will lose its electron and so be ionized. No lines will be formed since the atom doesn't exist anymore. As an atom, we have a proton-electron pair, so an ionized gas. Here are all the line series we can directly observe in the spectrum of a star. There exists a wide variety of astronomical objects characterized by a line spectrum. The line spectrum is often typical of the interstellar medium where the atoms, excited by stellar radiation, produce a spectrum consisting almost exclusively in lines. The latter inform us about the chemical composition of the gas, of which the nebula are made. The same is true of planetary nebula, where the different gas layers are excited by the radiation of the white dwarf star lying at the center of the nebula. And, closer to us, the polar aurorae we can see, during strong solar activity, display almost a line spectrum. We can see one here from the International Space Station. In this case, the atoms in the upper layers of the terrestrial atmosphere are excited by the collisions with the protons and electrons from the Sun that are captured in the terrestrial magnetic field. It is by losing energy through de-excitation that the atoms emit the polar auroras, which we have a magnificent line spectrum.